Inside every single one of us right now, there's a microscopic war going on. It is this constant, silent struggle that basically decides our health, how we age, and, well, our survival. So today, we're going to dive deep into this hidden world of cell injury.
And just to give you a sense of scale here, 37 trillion. That's more cells in your body than there are stars in the Milky Way galaxy. I mean, think about that. 37 trillion tiny living engines all fighting to stay online every single second of every day.
Because they do get hurt all the time. It's unavoidable. So what actually happens when one of these microscopic engines takes a hit? That question, that's really at the very heart of our health and, frankly, our survival.
All right, so here's our roadmap. We'll start with the cell's daily battle and meet a whole rogues gallery of threats. Then we'll pinpoint that critical moment, the point of no return. We'll watch the anatomy of a cellular breakdown, discover the shocking twist of when help actually becomes harm, and finally we'll connect all the dots to see why this tiny battle matters so much to all of us. Okay, so you know how every good story needs a villain? Well, in the story of our cells, there isn't just one, there's a whole gallery of them. These are all the different forces that are constantly trying to knock our cells off balance.
And these attackers, they come in all shapes and sizes. We can kind of group them into a few major categories. You've got supply chain failures. That's when vital stuff like oxygen just doesn't show up. Then there's good old-fashioned brute force, things like physical trauma or extreme temperatures. You've got poisons and sabotage from nasty chemicals. And maybe the strangest of all, internal conflicts, when the body's own systems, like our immune system, actually turn on themselves.
But if we had to pick the number one threat, the undisputed heavyweight champ of cell injury, it would be a supply chain failure. The technical name for it is hypoxia, which just means a lack of oxygen. And this usually happens because of something called ischemia, which is just a fancy word for reduced blood flow. So picture a city that suddenly has its power and water cut off. That's what happens to the cell. Without oxygen, its entire energy grid just grinds to a halt.
But of course, it's not just about oxygen. Cells can be beaten up by physical force, in an accident. They can be straight up poisoned by chemicals like cyanide or even just environmental pollutants. And let's not forget the invaders, bacteria, viruses. They're a constant threat. And then, in cases of autoimmune diseases, our own immune system gets confused and attacks our healthy cells. But here's the thing, all these different attacks, they all push the cell toward the same critical moment.
So when a cell gets injured, it reaches this fork in the road. It's a moment that decides everything. Can it recover, or is the damage too much? This is what we call the point of no return.
Okay, so look at these two paths. On one side, you have reversible injury. The cell's under stress, right? It might swell up a bit with water because its pumps are failing, and its main power supply, a molecule called ATP, starts to run low. But, and this is the key, if you take away that stress in time, the cell can bounce back. It can recover. But on the other path, you have irreversible injury. This is where the damage is just too severe. The cell's power plants, its mitochondria, are broken beyond repair. Its outer wall, the cell membrane, is full of holes. At this stage, there's no going back. Cell death is absolutely inevitable.
So what does this whole breakdown actually look like from the inside? Let's zoom in and follow our number one villain, that hypoxic attack, and watch the devastating cascade of failures it kicks off.
It happens like a row of dominoes falling, one after the other. First, the oxygen gets cut off. Boom. The cell's main power grid goes down. The cell panics. It switches to this backup generator, but it's way less efficient, and worse, it produces a toxic byproduct, lactic acid. As that acid builds up, all the machinery inside the cell starts to gunk up and fail. Next, the pumps that keep water balance break down, so water rushes in and the cell swells up like a balloon. And finally, protein production, the very function that could repair the damage, it just stops. It's game over.
Okay, so the problem is the cell is starving for oxygen. The solution seems obvious, right? Just restore the oxygen. Get the blood flowing again. Simple. Well, this is where our story takes a really dark, kind of shocking twist.
I mean, you would think that giving this suffocating cell a big gulp of fresh oxygen would be like the cavalry arriving to save the day. But here's the thing. Sometimes that rescue party ends up doing more damage than the initial attack.
This bizarre phenomenon actually has a name: ischemia reperfusion injury. It's one of biology's cruelest ironies. After being starved for a while, that sudden rush of blood and oxygen can paradoxically push an already injured cell right over the edge into irreversible death.
And this is a huge problem for doctors trying to treat things like heart attacks or strokes, where getting the blood flow back is critical. But it also comes with this terrible, hidden danger.
So what on earth is going on? Who's the new villain in this plot twist? Well, the culprits are these incredibly reactive and destructive little molecules called free radicals. When that fresh oxygen suddenly rushes back in, it triggers a massive, explosive production of these molecular vandals inside the cell.
And they just go on a rampage. See, free radicals are super unstable. They're desperate to steal electrons from any molecule they bump into, and that sets off this catastrophic chain reaction of damage. They chew through the cell's membranes, making them leaky. They smash up essential proteins and enzymes, shutting down the cell's machinery. They even attack the cell's DNA, its core blueprint, and tear apart its internal skeleton. It is just absolute chaos.
So we've been deep in the weeds here, down at the microscopic level. But why does this one tiny cellular battle matter so much in the grand scheme of things? Let's zoom out now and look at the big picture.
Well, when a cell dies from this kind of irreversible injury, it bursts open and everything that was inside spills out into your bloodstream. And these cellular contents, they're kind of like ghosts, evidence of a battle that was lost. And here's the cool part. Doctors have learned how to read the stories these ghosts tell. And this is exactly how it works in the real world. When you go for a blood test, doctors can look for specific enzymes that are only supposed to be inside your cells. So if they find cardiac enzymes floating around in your blood, that's a huge red flag that heart muscle cells have died. In other words, a heart attack. Same thing for the liver. If they see leaked liver enzymes, it points straight to liver damage. The whole story of our health is written in the chemical signatures of these dead and dying cells.
So here's the bottom line. Whether we're talking about a heart attack, liver disease, the aging process, or the effects of some toxin, it all boils down to this one fundamental story, repeated trillions of times over in our bodies. It's the story of a single cell, put under stress, trying its best to adapt, and sometimes failing. Understanding this battle isn't just abstract biology, it's the very foundation of medicine and health. Which leaves us with a pretty big question. What can we learn from its struggle?